All right, this is Electrical 2, NCCER Electrical 2, 10th edition, module number 26211-20, module number 11, control systems and fundamental concepts. So, getting straight into this, pull up some slides. So page 1, you've got trade terms. You should know, you should heard of all these trade terms, or probably done one of the labs where you know these trade terms. But brake, latch coil, make, mechanically held, normally closed or normally open, shading coil, unlatched coil. All these are going to be things that you need to know for this chapter. Make sure you read these trade terms. Very important for controls, especially if you want to get into controls in electrical. This is a good chapter to kind of leave off electrical 2, because maybe some of you guys are deciding to do residential. This might be the end of the line for you guys, and then you guys that want to go into some of this control stuff, make a little bit more money. This is the stuff that you have to absolutely know. So my first highlight is the first paragraph. It's going to be the first few sentences. A contactor is an electromagnetic apparatus that's designed to handle relatively high currents. The conventional contactor is identical in appearance, construction, and current carrying ability to the equivalent National Electrical Manufacturers Association, NEMA, size magnetic motor starter. The magnetic assembly and coil contacts holding the interlock and other structural features are the same. The difference is the contactor does not provide overload protection. Motor starter has overload protection, contactor does not. Motor starter has a contactor with an overload device usually on the bottom. Contactor is just making connections or not, no overload capabilities. Third paragraph, last sentence, down there where you see the normally open contacts. Contacts that are apart when the relay is de-energized are said to be normally open contacts. They're open, there's no energy, normally open. When they're closed, no energy, normally closed. Next paragraph, first sentence is highlighted. Notice that a shading coil has been added to the iron core in figure 1. Figure 1 should be what's up there on the bottom. That's this shading coil is down here at the bottom of the coil. Added to the iron core in figure 1, shading coils are used with AC relays to prevent contact, chatter, and hum. Just a short reason why they do that. Hopefully everybody remembers alternating current flows like this, right? So we have 3 points of 0 volts right here, and right here. So if we have AC current flowing through a shading coil, there's going to be this is going to be like one of your peaks, and then this is going to be the other one down here. But the 3 points of 0 voltage, that's going to mean that there's no electricity holding that coil together, and that shading coil makes up for these points of 0, and it holds it on there. To whereas if it didn't have it, whenever they hold these, like it would let go just a little bit and you would hear like a chattering. So a shading coil is like an accessory almost to a contactor, but they prevent that constant chatter and that hum. You hear hum in a contactor, more than likely it doesn't have the shading coil. Lighting contactors, 110. First sentence of lighting contactors is highlighted. Filament type lamps, examples tungsten, infrared, and quartz, have inrush currents of approximately 15 to 17 times their normal operating currents. Third paragraph, the whole thing's highlighted and it goes into page 3. Lighting contactors differ from standard contactors in that the contacts are rated for high inrush currents. A holding circuit interlock is not normally provided because this type of contactor is frequently controlled by a 2-wire pilot device, such as a time clock or a photoelectric relay. So either a timer or a photoelectric relay are turning these lamps on. Also on page 3, right-hand side of page 3, that big paragraph on the right-hand side, first sentence is an online test question. I think we've got several online test questions in this chapter. Another application of a magnetic relay is the use in emergency lighting circuit. So emergency lighting circuits use magnetic relays. You've got table A or table 1A and B. You're going to have questions that come out of these for the different size NEMA contactors, like how much, like what the sizes are, what the voltage are, and what the amps are. You're going to have questions come out of that, so make sure that you highlight pages 4 and 5 to get review question highlights out of them. Page 6, 120. Forward and reverse motor contactor connections. If you've done the motor lab out there, this should be easy for you. But you should recognize some type of circuit like this, where you have your forward contacts and your reverse contacts. On your skill out there, they put the reverse on top, but it doesn't matter as long as they're connected the same. So I'm going to share my highlight and I'll talk about it. So the highlight 120 is the second and third paragraph. So starting with the second paragraph, as seen in the power circuit figure 6, the contacts F on the forward contactor, when closed, connect lines L1, L2, and L3 to motor terminals T1 through T3 respectively. As long as the forward contacts are closed, the mechanical electrical interlocks prevent the reverse contacts from being energized. When the forward contact is de-energized, the second contactor can be picked up, closing its contacts R, which reconnect the lines to the motor. Note that by running through the reverse contacts, L1 is connected to T3, L3 is connected to T1. The motor will now run in an opposite direction. So, all that to say, whenever you have forward turned on, these three are running forward. You should hopefully know by now the way to reverse a three-phase motor is just to switch any two of the phases. You switch all three, you're switching all around, and it's still going to go the same direction. So, with the forward contacts in, L1 is going to T1, L2 is going to T2, L3 is going to T3. If these forward contacts are all three of them are closed. If I open them up, turn it off, and I hit my reverse button, now what's going to happen is my line 1 is going to go here. It's not going to go through my forward contact, so I'm going to have voltage here, but it's not going to pass through there because that's normally open. It's going to come down here, go through my closed first reverse contactor, and go through here and hit T3. So L1 is going to go to T3. L2 is going to come in, hit this, go through R2, and then come up and hit T2. So that's going to stay the same. L2 is staying with T2, and L3 is coming down, hitting your reverse contactor and going up and hitting T1. So essentially what we're doing is by running through the reverse contacts, we're switching line 1 and line 3. And that's typically how you do it in a factory. You're switching 1 and 3, and 2 is staying the same. Still in that same section, but on page 7, that last paragraph, the whole thing is highlighted. Manual reversing starters employing 2 manual starters are sometimes used, as in the magnetic version. The forward and reverse switching mechanisms are mechanically interlocked, but since the coils are not used manually operated equipment, electrical interlocks are not furnished. Mechanically held contactors, 130. The whole first paragraph is highlighted. In a conventional contactor, current flow through the coil creates a magnetic pull to seal in the armature and maintain the contacts in switch position. That is, normally open contacts will be held closed, while the normally closed contacts will be held open. Because the contactor action is dependent on the current flow through the coil, this contactor is described as electrically held. As soon as the coil is de-energized, the contacts will revert to their initial position. Last paragraph on page 8 is important. I've got 2 highlights that come out of that one paragraph. Mechanically held relays and contactors are used when the hum of electrically held devices would be objectionable, such as in an auditorium, a hospital, a church, and so on. So places that are quiet need to have these mechanically held relays, and that's so that, like, that shading coil only does so much. Like it's still might still have a little bit of chatter, but if you do a mechanically held relay, that stuff's going to stay together and it's going to hold together, and you're not going to have that hum whereas you would with an electrically held relay. Moving on to section 2. Section 2, relays. First paragraph of relays. The whole thing is highlighted. Got a couple questions coming out of that first paragraph on page 9. Control relay is an electromagnetic device that's similar in operating characteristics to a contactor. The contactor, however, is generally employed to switch power circuits at relatively high currents. Relays are normally used in control circuits, and consequently their lower ratings, 15 amp maximum for relays at 600 volts, reflect the reduced current levels at which they operate. So these are like your little ice cube relays and stuff like that. Moving on to, on the right-hand side of the page, that first full paragraph on the right-hand side of the page, I've got the first, is that one sentence, first sentence highlighted. Besides controlling electrical circuits, some types of relays are also used for circuit and equipment protection. Not all one sentence. For example, thermal overload relays are intended to protect motors, controllers, and branch circuit conductors against excessive heating due to prolonged motor overcurrents. This could be bad bearings or something like that, up to and including locked rotor currents. So that's like your motor startup and stuff like that. You're going to have very high amounts of current flowing through this stuff. Flipping the page, still in the same, or moving on to control relays 210. Flipping the page to page 10, so you can get some circuits and stuff on page 10 to look at. On page 11, the whole first paragraph is highlighted. Got a couple important highlights in this one paragraph. Figure 9. So that's this figure, I think right there. Figure 9 up there on the board or at the bottom left of your page 11. Figure 9 represents another use of relays, which is to multiply the switching functions of a pilot device. A pilot device with a single or limited number of contacts. Key in on the rest of this highlight. In this circuit, a single pole push button contact can, through the use of interposing 6-pole relay, control the operation of a number of different loads, such as a pilot light, starter, contactor, solenoid, and timing relay. Up at the top of that, I wrote the interposing 6-pole relay. That's the same thing as a multi-pole relay. You need to know that those two things are the same thing. Interposing 6-pole relay is the same as a multi-pole relay. Skip a paragraph, and that third paragraph on page 11, the whole thing is highlighted. Relays differ in voltage ratings up to 600 volts, number of contacts, contact convertibility, physical size, and attachments for accessory functions such as mechanical, lighting, and timing. All that. So there, you can have different things for different relays and stuff. Moving on to 220, timers and timing functions. These are the control relays. Like normally you're going to have, they're going to look like this. It's going to be some type of ice cube relay. We get into those quite a bit in instrumentation if you guys are interested in that. Like I said, like those are used a lot more in instrumentation, and not a lot more, but definitely more in controls, more than like residential wiring and stuff like that. But 220 timers and timing relays. On the right hand side of page 11, that first full paragraph or second paragraph of the section, the first sentence is my first like 5 lines for the first sentence. A time function is useful in applications such as lubricating systems of large industrial machines, in which a small oil pump must deliver lubricant to bearings of the main motor for a set period of time before the main motor starts. Next, the rest of that paragraph is a separate highlighted. Furnaces also incorporate fan on delays to avoid blowing cold air into space whenever the system starts up. That's like your AC or your heat at your house, right? I know we don't use heat for a lot of months down here in Southeast Louisiana, but when you turn your heat on, whether you have gas or electric, like you can, if you have gas, you can hear the burner turn on. It has to heat up the pipes, and before it does before it turns on the blower motor. Because if the blower motor turned on, you'd be blowing cold air, like the cold air that's in your attic or wherever your HVAC unit is. You're going to blow that throughout your house. Whereas if you let that heat up and you have a timer function that says, hey, don't turn on for 30 seconds till we got these pipes and stuff warmed up and good to go. Solid state relays. Finally got some of those in the shop for everybody to look at. 230. These are things, these don't have any moving parts. 230, I've got the third sentence highlighted. One common use, and again, this online test question. One common use for solid state relays is the I/O rack of a programmable controller, which is a controller that can be changed by reprogramming rather than requiring an extensive rewiring of control systems. So everybody, you use solid state relays. This is the big Slick 5000 Allen Bradley PLC, but this is what you're using solid state relays for rather than electromechanical relays where you're having to switch wires. This you can actually just switch by changing the programming. Down at the bottom of page 11, right after that note is highlighted, the following are some typical solid state relay control circuits. I've got the long highlight. Almost all of the first bullet point is highlighted. Power transistors for DC loads. In this DC circuit, a power transistor is used to connect the load to the line as shown in figure 13A. I need to get that, see if I get that figure 13A. So that's the top one on the board. In this DC circuit, a power transistor is used to connect the load on the line side shown in figure 13A. So the line side, so that's my line side over here. Power transistors used to connect the load to the line as shown in figure 13A. This is an opto-isolated relay with a light emitting diode. So your light emitting diode is right here. So this is an opto relay. Your light emitting diode's right here. So there's not anything that actually moves. Something in the solid state relay just turns on a light essentially. With a light emitting diode, LED connected to the input or control voltage. This is a common circuit arrangement in solid state relays, and relays that use this coupling method are referred to as opto-isolated because the load side of the relay is optically isolated from the control side of the relay. Since a light beam rather than electricity is used to control the relay, no voltage spikes or electrical noise produced on the load side of the relay can be transmitted to the control side of the relay. Moving on from there, different types still have more. That's the first, that's the A one. And then moving on to page 14, I don't have anything in the triac controlled AC relays, but those are used quite a bit. The third bullet point, the whole thing is highlighted. Another method of controlling solid state relays in the AC circuit is to use small reed relay to control the output, as shown in figure 13C. In this circuit, small sets of reed contacts are connected to the gate of the triac, and the control circuits connected to the coil of the reed relay. When the control voltage sends a current through the coil, the magnetic field produced around the coil of the relay closes the reed contacts and activates the triac. Unlike opto-isolated relays, like what we just talked about, this type of solid-state relay uses a magnetic field to isolate the control circuit from the load circuit. Bimetallic overload relays. These are used a lot. 241. Simplified bimetallic overload relay is shown up on the board or in figure 14. My highlight for these is the last paragraph in that section right before 242. That last paragraph, first sentence is highlighted. The ideal overload protection for a motor is an element with the current sensing properties that are very similar in the heating curve of the motor. It protects and will open the motor when the full load current is exceeded. So what they're saying is like this heater element acts the same as like the internals of that motor. And whenever there's being too much current being pushed through that, it'll open up so that it acts, so it knows, it acts like the motor, and it knows when too much current is flowing through it. 242 fuses versus overload relays, flipping over to page 16. That first small paragraph on page 16 is highlighted. Dual element or time delay fuses can provide a motor overload protection, but have a disadvantage of being non-renewable and must be replaced once tripped. Fuses have to be replaced. Overload relay classifications 244. First sentence is highlighted. Overload relays can be classified as being either thermal or magnetic. Overload relays can be classified as being either thermal or magnetic. Next paragraph, the whole thing is highlighted. The melting alloy assembly of a heater element and solder pots are shown in figure 15. The motor load current passes through the heater element. So that's talking about what's up here on the board. Current passes through this. This is our solder pot on the back. Ready for that? Motor load current passes through the heater element. When it exceeds the designated capacity of the heater, it melts an alloy inside the solder pot. The ratchet wheel will then be allowed to turn the molten pool, and tripping the action of the starter control circuit results, stopping the motor. A cooling off period is required to allow the solder pot to harden before an overload relay assembly may be reset and the motor service restored. So very simple device, but very effective device. That solder inside that pot is going to melt only at a certain temperature. When we hit that temperature, it melts, and you can see that wheel on the side that spins. Asked me to show you all those in the lab. Like we can take those off, and you can see those melting alloy thermal units for these motor starters. Relay selection 245. First sentence is highlighted. When selecting thermal overload relays, the following must be considered. First bullet point, all the bullet points are highlighted, but the first one I've got keyed in on. The motor full load current must be, like that's the first thing you're going to look at. The type of motor, and then the difference in ambient temperature between the motor and the controller. So ambient temperature does make a difference. Still talking about selection, moving on to page 17. That middle paragraph on the left-hand side of page 17, second sentence, second and third sentence are highlighted. An alarm signal is sometimes required to indicate when a motor is stopped due to an overload trip. Also, in some machines, particularly those associated with continuous processing, you may be required to signal an overload condition rather than have the motor in the process stop automatically. So just know that this stuff, these relays can be hooked up to alarms that let you know whenever stuff's tripped out or about to trip. 250, troubleshooting relays. Second paragraph, first sentence is highlighting. The operating coil is usually designed to operate the relay from 80 to 110% of the rated voltage. So voltage shouldn't be a big deal in operating these relays. Because that's a wide range of operating voltages. Same paragraph, last sentence is highlighted. Increasing the armature spring force where the magnet gap will require higher pull-in voltage or current values and result in a higher dropout value. So if you increase the tension of the spring in these relays, you're going to have higher dropout values. Table 2A, that's where you're going to get your contactor and relay troubleshooting chart. You're going to have a test question come out of that. I do have that second, the failure of equipment to start with the contactor closed. One of the options is the one contact not closing. This is not very common. If you have 3 contacts or something like that, one of them not closing isn't going to be very common, but it can happen. It's just not going to be, more often than not, I would think one of the other, like the contacts being burned, I have found to be more of a problem than one contact not closing. But just know you're going to have questions come out of those tables. And then we go on to section 3. So section 3, last section of the book. Moving on to low voltage remote control switching systems. My first highlight in section 3 is in the first paragraph, second sentence. Basically, these systems use special low voltage components operated from a transformer to switch relays, which in turn control the standard line voltage circuits. That's all I got for section 1, but you can see that figure 16 shows that up in the top right of your page or up here on the board. Page 22, 310. System components and operating characteristics. I got 2 highlights that come. I highlighted pretty much everything on page 22 and 310, not the sentence that's going into the next page. The relay is the heart of the remote control switching system. It employs a split low voltage coil to move the line voltage contact armature to the on or the latch position. As illustrated in figure 18, the on coil moves the armature to the right when a 24-volt AC control signal is impressed across the leads. So that's figure 18 that they show up on the board. So it says as the on coil moves the armature to the right. So on, it's talking about this one right here. It's going to move the armature to the right or up. But it's going to connect your line and load is what it's going to do for that relay. Oh, on coil. That's what they're saying. They're going to move this to the right. So this is your on coil, off coil. So whatever one you're heating up is going to move that armature back and forth. Then they're just flipping it vertically, showing the next one. Flipping the page 24, you got power supplies, switches, both are going to be important, but I don't have any highlights in. Moving on to 313, master sequencer. This is going to be more important for like lighting stuff. But 313 master sequencer, first sentence is highlighted. The master sequencer allows relays to be controlled as a group while still allowing individual switch control for each one. So you could turn like all the lights on in the building, but then you could shut off different rooms as needed. Nothing under operating characteristics, but you guys can read through that. Planning a remote control switching system, 320. Flipping over to page 26. I don't have anything on page 25. 26 and 27 don't have highlights, but you can read through those. They kind of show the different switches and stuff like that. And they go through the steps on how to plan the remote control switching system. I do have some of the symbols on page 28 highlighted. So flipping over to page 28, you've got these symbols. I've got the low voltage transformer symbol highlighted. The still on the left side, the relay with a pilot switch. Spec grade 2 refers to the number of relay highlighted. The one directly under that is highlighted. Low voltage switch with spec grade standard type. And then if you go right to the right of that on the right-hand side of the page, I've got the separate pilot light symbol highlighted. All those you're going to need to know for your module reviews and quizzes. 321, enclosures. First sentence of enclosures is highlighted. The enclosures should be placed in a location that is easily accessible but hidden from sight. So that's the first sentence of that paragraph. The last sentence up in the top right is also highlighted. The panel itself should be mounted at eye level between 2 studs. So at eye level between 2 studs, but out of sight. Switch points 322. The last sentence on the page is highlighted. The process is repeated for the DC common lead, last couple sentences. DC common lead. When this wiring method is used, the DC positive and common lead will have the same color throughout the system, and future connection mistakes will be minimized. Flipping over to page 30 and 31. So this is just talking about different switch points. They're going to give you this picture, like you can see where the different, like S, whatever's labeled S is a switch. So you can have like a single switch or a switch or a light that's controlled from multiple switches. You've seen this stuff before. But still in this section, on page 31, the top right paragraph, the whole thing's highlighted. I've got a section review question and an online test question that come out of this one paragraph. The low voltage wiring should also be kept apart from the high voltage wiring whenever possible. If the cables must be placed in parallel runs, they should be separated by at least 6 inches. Otherwise, the noise, key in on the noise generated. This is from the EMF from power signal cables. generated from the high voltage conductors could seriously interfere with the operation of the low voltage system. You have high voltage wires that are in parallel with low voltage wires. That's going to have EMF or electromagnetic interference, EMI, EMF, same thing, on the other cable and create noise. Not good. Definitely not good for instrumentation cable and stuff like that. That is all my highlights for this chapter. Please let me know if you have questions.